Hi all. Our team is analyzing and redesigning a 3D printer this semester. There are many types of 3D printers, but we are specifically analyzing a fused filament fabrication or FFF printer, where various types of materials, including plastics, are melted layer by layer to create a 3D object. 3D printers are used by hobbyists and industry professionals alike to manufacture products with small batch sizes, design prototyping, and to manufacture complicated parts not otherwise conventionally manufacturable. We chose to analyze a simpler and cheaper 3D printer that uses T-slots with rollers to move in the X, Y, and Z axis. But due to complexity, we are focusing our analysis on just the X-axis subassembly pictured on the right of the screen.
Here's the exploded view of our product design. Here you can see each of the components labeled, given a number and a name, which will be used for further documentation in this presentation. To begin our functional analysis, we start with a FAST diagram. Our primary objective is to produce an item. And in order to do that, we need to melt material, which will involve adding material itself and then adding heat to said material. To adhere the material using some sort of cooling method to either the plastic that came before it or the build plate itself, and then to traverse the print space, which will involve controlling the movement of the structure as well as providing some sort of support for the printing head and the rest of the motion. We also want to ensure dependability by eliminating any inconsistencies in our prints. This will involve removing vibration and limiting any excess motion. We also want to increase the usability and usage of our machine by providing cooling to our work head, which will allow for faster and more higher volume prints. We also want to ensure convenience by giving access for maintenance and by facilitating adjustments to any components that will require maintenance themselves.
To understand the assembly sequence analysis, we made two fishbone diagrams. The first one, as you can see, we grouped more parts together. We did that from the explode view diagram. We went on arranging parts from left and right. In the first one, you can see that there are only two parallel branches, which with more parts being grouped together. In the next one, we divided into further smaller sub-assemblies. That way we could arrange the parts faster. So in this slide, we analyzed both our assemblies. The it was shown that the sequence B was better as there was smaller grouping to test better sub-assemblies and fastening.
Here you can find our functional component mapping matrix, where we took the objectives from the FAST diagram and combined them with our assembly diagram given in the fishbones, and provided a rating or a functional mapping for each of our FAST objectives to our fishbone assemblies and each of our components in there. From there, we created a bill of materials, which evaluated each of the components, all 48 of them, into what their relative costs for manufacturing and materials. Each of the screws and stuff like that were considered to be purchased components and did not require any additional costs, which came out to a $134.32 of total cost for our component. Using the quad chart and combining the fishbones and the BOM, we were able to come up with what components we needed to redesign, which were primarily structural, as those were easy to redesign and more relevant. Other components that were more expensive, such as the motors and the hot end, were purchased and could not be redesigned readily. And then additional components such as screws and inserts were decided to try to be eliminated as best we could.
Most functions from the FAST are the same for both primary and secondary customer groups, except for the heating, material addition, and vibration removal aspects. So all the parts that correlate with the customer group functions are listed, but the T-slot frame, the hot end, the bed leveling sensor, and the fan cover being the modules. And all the modules are pictured on this slide, and do note that the bed leveling sensor is only added to the secondary assembly and is not included in the primary assembly. And these modules interface with the hot end mount, X-axis mount, and Z-stent. The Z-stent and X-axis mount fasten both the primary and secondary T-slots to the Z-axis T-slots and allow for stability while moving. The hot end mount accommodates for both primary and secondary hot end setups.
Here is our product family assembly sequence. The first assembly sequence includes two parallel assemblies, which involve pretty much zero branching and no delayed manufacturing. In the second one, we decided to group them into sub-assemblies, which allows for delayed assembly of the motor X bracket, Z-stent, hot end mount, and E-plate, as well as the fan itself, to continue to create two final assemblies.